He was a postdoc at the Niels Bohr Institute in Copenhagen. And after 4 years, he has joined as a faculty fairly recently in October 2020 at TIFR. His research interests are astroparticle physics and cosmology, data analysis, information theory, statistics, and machine learning. So we will hear about the cosmological principle and the missing rest frame of the universe from Ramesh. So Ramesh, please take over.
Thanks for the introduction, and thanks for inviting me to give this seminar. It's a huge honor to be speaking in front of at a very esteemed institution. I'm going to tell you about some work I've been doing over the last 2 or 3 years with collaborators who include Nathan Seacrest, who's an astronomer at the US Naval Observatory, Sebastian von Hossegger, who is now a postdoc in Oxford, Jacques Collin and Roya Moheai, who are at the Institut d'Astrophysique de Paris, and Subir, who is also at Oxford, who you must have heard of. So the cosmological principle, foundational idea of the modern lambda CDM model, the Robertson-Walker, Friedmann-Lemaitre, Robertson-Walker cosmology, it is the justification, which is the idea that the universe has no special direction or special positions in it. It looks the same in all directions, and if you move a little bit, it doesn't look all that different. Now, of course, we know this is exactly true because the planet and the galaxy, etc., exist. So then the idea is that it statistically looks the same in all directions and is also statistically homogeneous. And then there's also an idea called the Copernican principle, which is that we are typical observers. From the point of view of this talk, it is going to be that there is a frame in the universe in which if you look, you will count roughly the same number of sources in all directions, as long as you're looking deep enough and at large enough angles. Now, a principle like that has not been introduced simply because it is reasonable to assume it is true, etc. For example, there have been many relativistic world models proposed in the early days of general relativity. And because the observed data is essentially insufficient, you don't have data all over the sky, etc., you have to assume some model, and then you get so that is how you get the cosmological principle. So the idea is that apart from local irregularities, the universe presents the same general aspect at every point. So there was something called the perfect cosmological principle, which was that we were in no special place in either space or in time. And this has obviously been abandoned since the discovery of the CMB, because now we accept that the universe began with the Big Bang. But the real reason for the cosmological principle is actually written down in Weinberg's Gravitation and Cosmology textbook. For our adherence here to the cosmological principle is not that it is surely correct, but rather that it allows us to make use of the extremely limited data provided to cosmology by observational astronomy. And if the data will not fit this framework, we shall be able to conclude that either this cosmological principle, one of the founding principles of modern cosmology, or the founding principle of modern relativity, general relativity, is wrong. Nothing could be more interesting. And the reason we have the Copernican principle is that all information we can gather about the universe is actually contained within a past light cone. It is there are some limitations to human knowledge, and we cannot move over to cosmological distances and sit in the Virgo cluster or the Andromeda galaxy or whatever and see if the universe looks the same. So we must assume that our position is not special in any way. And this is the kind of Copernican principle that Milne proposed. The universe must appear to be the same to all observers. This is the Copernican principle. So far I told you of this as a foundational idea and assumption. Apparently today this you don't have to worry about this at all, because the Planck satellite actually shows us the universe is extremely isotropic. So we have measured the monopole temperature of the cosmic microwave background, and it is about 2.7 Kelvin. And the idea is that if you check how that varies in different directions in the sky, the variation is only about 1 in 100,000. So if you quantify that as a power spectrum, it is you get these microkelvin scale numbers, and you can the power spectrum can actually be very well fit by some kind of a theory. And this theory, the parameters of this theory now tell us that the universe is just 5% the stuff we know about in particle physics, remaining 27% dark matter, which we look for in indirect detection, direct detection, at colliders, etc., and 68% dark energy, which is causing the expansion of the universe to accelerate. One of the things I want you to notice about this image is that it goes only down to 90 degree, the L mode of 2. Why is the L equals 1 mode not here? That's because it actually wouldn't fit in this diagram, and this is because the CMB is actually not that isotropic. There is a dipole in the CMB, which is about 1 in 1,000. So it's 100 times larger than all the things that you believe are primordial, that you think is a picture of the last scattering surface. So there is an anisotropy in the cosmic microwave background that's 100 times larger than that. And the explanation for this anisotropy is that this is purely kinematic, in the sense the universe is actually isotropic. It's just that with respect to the frame in which the universe is isotropic, we are moving with a velocity of 369 km per second. And by V, I mean the rest frame of the sun, because the missions we launch actually, they are either in Lagrange points around the sun or so. So all the data are corrected to the heliocentric frame. And so the sun is moving with this velocity with respect to the frame in which the universe looks isotropic. And so this is apparently all you need to think about. This is that it is a special relativistic boost, purely kinematic, nothing to worry about. What is the origin of this motion? We can actually use other techniques in astronomy like parallax, etc., to measure how fast the sun is moving around the galaxy, how fast the Earth is moving around the sun, etc. So the Earth is moving around the sun with a 30 km per second velocity, which actually has nothing to do with this, because like I said, this is in the frame of the sun. The sun is moving around Earth is moving around the sun with a 30 km per second velocity. The sun is moving around the galaxy with something like 220 km per second or so. And this is an orbit that takes about 260 million years. For most of the time we've been looking, that vector is fixed. And then it turns out that the galaxy is falling towards Andromeda. And if you take the rest frame of the local group, which is the barycenter of Andromeda and the Milky Way, that is moving with a fantastic velocity of about 600 km per second, roughly in the same direction, because the velocity of the sun around the galactic center and the velocity of the galactic center with respect to the cosmic microwave background are actually counter-aligned within 7 degrees or so. So, 600 km per second is a pretty big velocity. So this is what we understand. But let's see if the CMB dipole is actually purely kinematic. One of the tests for that is that if there is a frame in which the universe actually has a very isotropic distribution, so sigma rest is isotropic, then if you're moving with a velocity with respect to that frame, due to two special relativistic effects, one being aberration, which is that lengths in the direction of your motion are contracted and consequently angles shift a little bit. This is a small effect in the direction of your motion. That's called special relativistic aberration. The other is that if you compile a catalog that's flux limited, that is, you take only sources that are above a certain limiting flux. We know that astrophysical sources emit in power loss, and when you evaluate the flux, you're basically integrating within a band. If you're moving towards a source, that source gets Doppler shifted, and as a result, fainter sources become within your band. And as a result, you get additional sources in the direction of your motion. So the sum total of these results is that if you have an isotropic distribution in the rest frame, you get a dipolar modulation due to these two effects, which leads to more sources being seen in a flux limited catalog in the direction of your motion. This equation was written down by George Ellis and John Baldwin, 1984. It's a very interesting paper. I would encourage everyone to read it. They derived this equation and they conclude by saying if the standards of rest determined by the microwave background and the number counts were to be in serious disagreement, one would have to abandon either the idea that the radio sources are at cosmological distances, or the interpretation of the cosmic microwave background radiation as a relic radiation from the Big Bang, or the standard FLRW universe models. Thus, comparison of these standards of rest provide a powerful consistency test for our understanding of the universe. Now, so if there is one message I want to convey from this seminar, it is that I believe the situation that Ellis and Baldwin anticipated in 1984 has finally arrived upon us. We can, if you take an arbitrary catalog of sources in the sky, of galaxies, quasars, whatever, it has some redshift distribution like this. You can see different types of dipoles in it. There is the kinematic dipole, which is what Ellis and Baldwin spoke about, which depends on your velocity. It depends on the spectral index of the sources. It depends on what is called the index of the flux function. I'll show you later. There is a short noise dipole, which is just a square root of n effect, because you need a large enough number of sources of the order of 1 million sources to be able to resolve this. There is actually something called the clustering dipole, which is that if this is a very shallow catalog, then we know on small scales the universe is not really isotropic. So you expect a local isotropy due to structure. And then there's something, you can have dipoles due to foreground if you don't handle your star contamination, etc. better. I'll talk to you about mainly 3 papers. The first one is a deep radio galaxy catalog, in which essentially the expectation for clustering dipole and for star contamination, etc. was 0. And we had a mildly statistically significant anomalous result. Then we looked in galaxies, but it was too shallow, so this clustering dipole is a major contaminant and we can't be sure. Then we looked at high redshift quasars, which has more recently been published, has been covered in New Scientist, etc. And here, because it's a very deep catalog, the clustering dipole is essentially just 1% of what we observe. And all of these are anomalous with the idea that the CMB dipole is purely kinematic. And one of the things is that means matter in the local universe is flowing, which has some general relativistic effects. We looked for that effect with the same supernova catalog which people discovered dark energy, or which is evidence for dark energy. And we found actually a very interesting result, which led to a debate in literature. Since this is Friday afternoon, I think you'll find this debate quite entertaining. More recently, we have been an invited review that we were asked to write has, it's been accepted. You can find it on arXiv, the whole thing. It also these things also have implications for what you've heard of called the Hubble tension. So I'll tell you about that. So we started off by looking at what is called the National Radio Astronomical Observatory's Very Large Array Sky Survey. Ashok Singhal had already looked at this and found that the dipole in this was very large, but you can see that this survey is not complete in the sky. So there could be biases to the estimators that you use simply because you don't have a complete sky. And so this is what is called the index of the flux function, the slope of this line, what I called x in the in this equation, or in this equation. So this is obviously not a complete catalog, but it is. Can
you repeat what was the x again? I didn't quite catch what that was.
It is the slope of this curve. So this is the number of sources above a threshold as a function of your flux threshold, and that comes into it leads to your number count dipole being modulated by that, because as you move towards the source, fainter sources come into your band and you count more sources in that direction. So this catalog is obviously not full sky, so we patched it together with an 843 megahertz survey of the southern sky, which has the same beam size as this catalog. It was meant to be a sister survey. Together there is about 1.9 million sources, but it turns out they are not really, like, the survey does not claim to be complete other than about 10 millijansky. So we had to cut at 10 millijansky. Also, the two catalogs have a region of overlap, like NVSS is complete down to minus 40, and SUMSS goes up to minus 30. So there's 10 degree of overlap where you can cross-match sources, study all sorts of systematics, and we did all of that. And we don't actually know the redshifts of these sources, but these are bright radio galaxies, and the idea is that most of them are at a redshift of 1. to estimate a dipole in a catalog like this, the simplest thing would be to just cut the sky into two hemispheres, check for the difference in the number of rows on both sides. This is, of course, very nice to visualize, etc., but it turns out it has high statistical bias. You can also use a linear estimator like this by just adding up unit vectors corresponding to each source. This has lower statistical bias than this, but it is still biased if you don't have the galactic plane, etc. Then there are quadratic and least square estimators where you explicitly look for a dipolar pattern given by dipole templates. And so we did this analysis first with this NVSS SUMSS patched together catalog. And what we found was that the dipole is actually within 10 degree of the CMB dipole. But if you use that Ellis and Baldwin formula and the X and alpha derived from the data itself to estimate the velocity, it turns out the velocity is roughly 4 times larger. Now you can see that there's a large error bar here. That's because this final catalog is only about 600,000 sources, so there is a big short noise dipole. And so you have to use, you have to scramble the data to see what the statistical significance of is, and this is only about 2.81 sigma. I am primarily a particle physicist, so this is a statistical fluctuation for me, but it's mildly interesting. For example,
sorry, Ramesh, can I interrupt? Can you please go back to the previous slide?
Yeah.
Yeah, can you please explain your estimator a bit in more detail? I didn't quite understand.
So the estimator that is visualized here is the hemispherical count. So it is the difference in number counts in both halves of the sky.
Oh, that's the one on your left hand side.
Yeah, this is actually you just take on S2 a unit vector from the center corresponding to the direction of each source, and you add this up. And that this is a biased estimator for your dipole, but you can study the bias from Monte Carlo, etc. But it has lower bias than this. And then these are explicit template fits. You are fitting for a dipole-like template called, and so this is called the quadratic and the least square estimator.
So for example, in the lower right corner, that one,
yeah,
the template and the A's, how do you fix them?
So A1, etc. are fit parameters, and you minimize this term. NP is the number of sources in each pixel.
Okay.
So the number of sources in each pixels, you subtract from that the template corresponding to the L equals 1, minus 1, and 0 mode, M equals 1, minus 1, and 0 modes of the dipole. And each of them have a normalization to give, which corresponds to these A. So you minimize this with respect to these 4 A values, and the ratio of A1 by A1 by A0 is this one is for the L mode, is the size of your dipole. This is actually, because it's the least squares estimator, is unbiased, and we have studied that using Monte Carlos, and it looks quite unbiased. Okay. So like I said, with NVSS, this is just 2.81 sigma. It looks like a statistical fluctuation, but others have done similar exercises with other radio catalogs. For example,
so one more. Sorry. So your X and alpha both come from your sources. Is that correct?
Yes.
Okay. So the velocity is something that, let's say, so in the Ellis Baldwin formula that you wrote down.
Yeah.
So sigma. What is a sigma? Sigma. What is sigma here on the left? The sigma rest and the sigma observation.
This is the number of sources per solid angle.
Okay, I see. Okay.
And that is modulated.
So the point that is being made is that so this observed thing. So what is it that you will be measuring the sigma observed? I guess, is that correct?
Yeah. We are essentially we are fitting for we are essentially fitting for sorry, where is that the estimator? Yeah, we are fitting for A0. So it depends on which paper I'm talking about. We have used these two estimators for NVSS, and for the CatWISE we actually use this estimator where you fit for A1 and A0. This is the monopole term. This is the dipole term. You can, of course, expand this to include also quadrupole, octupole terms, etc., which we are now doing for a follow-up paper, but that doesn't really affect anything. So the question is how big is the dipole in the number counts of sources in a sky map?
Yeah. So So I mean, so that's the kind of about the details in some sense. But I'm saying that very broadly speaking, the sigma theta is what you get from the sky. Is that correct?
Exactly. It's just the number of sources in each direction in the sky.
And then the claim is that you're trying to, and from the sources you get alpha and x.
Exactly.
And then whether the V actually matches what you expect from the CMB dipole is the contradiction.
The V, so in the case of NVSS, the V does not match what we extract from the CMB dipole.
Yeah. I mean, yeah, that's why that's why I'm saying that it's a contradiction. So you get this, the observed sigma together with this information about the sources from X and alpha, together all of these things together should reproduce your the V. And if it doesn't, you have tension with the CMB dipole. That's what the claim is. Is that right? I'm just trying to make sure I understand it.
Exactly, it is.
Yeah. Okay, thanks.
So at 2.8,
sorry, can I ask a question? Sorry, so what is this V here? Velocity? What is the velocity? What does it represent? I'm sorry for this.
It is a velocity I am measuring using this equation. It is in tension with what we believe is our velocity with respect to the rest frame of the universe. I will later.
So that is around 600, right? That's what you said.
It's 369. 600 is for the local group. We are carrying out all of these missions from Earth, which is close, which is
so
close
369. Okay, all right.
Yeah. So so this was, Carlos A.P. Bengali, who is now at University of Geneva, and Roy Martins and so on, important cosmologists. They have looked at, for example, the catalog of TGSS, which is by the GMRT telescope in Ooty. And there they actually find a 5.1 sigma axis, where if you try to interpret as velocity, it's as high as 1,600 kilometer per second in this paper. More recently, Dominic Schwarz, he's very interested in this. They have written this paper, Siewert et al., where they've analyzed 4 radio catalogs, including NVSS, SUMSS, and they study all. And they conclude that for all analyzed surveys, the observed cosmic radio dipole exceeds the expectation derived from the CMB dipole. So we decided that, when we put out this paper, it was not very statistically significant. And also people say, oh, this is a ground-based catalog. There could be all sorts of systematics. So one of the things to do is check if we see something similar in space-based observers.
Sorry, Ramiz, before you go any further, can I ask basically, how do you quantify the systematic uncertainties here? Like, this is just purely statistical statement, right?
No. So statistics, systematics was about 180 kilometers per second, and statistics is another.
And how did you arrive at the 180 kilometers per second?
It's actually quite hard to do that, but we did things like we removed all local sources according to Tomorrow's redshift survey. We removed the supergalactic plane. We see how much scatter there is in the magnitude of the dipole, and we just take the maximum value.
So as a percentage of your errors, so what percentage is statistical and what percentage is systematic?
It's roughly 50-50 for this catalog.
Okay, thanks.
We're now quantifying, overlap with other catalogs, etc. So I'll keep you updated. We looked at this Widefield infrared survey explorer, which actually had an initial mission of 10 months in which it looked in 4 bands at the entire sky in infrared. It has a very unique survey strategy. It always looks in a direction that is perpendicular to the direction of the sun to keep background light, etc. Exactly constant, so that you have uniform sky coverage. And after the 10 months, it ran out of cryogenic fuel, so it was running only with the first 2 bands operational. I don't really understand telescopes and cryogenic fuels, etc. So I don't know why, but so it has later on produced even better catalogs now there is a 1.4 billion sources catalog. When we first looked at this, it was 746 million sources catalog. And the vast majority of these objects are unfortunately stars, which stars are not at cosmological distances, so they're not useful for this. And even after you use standard techniques available in literature to apply magnitude cuts and reduce star contamination as much as possible, etc., you see there is a clear excess of stars along the galactic plane. We looked at what is called the apparent motion. So this survey has imaged each point in the sky multiple times, at least in twice. So you can look at how different the astrometry is at different points in time and fit for the change, which if there are only two images at each point of the sky, then you cannot tell the parallax and proper motion apart. But once you remove the galactic plane, most nearby sources, especially stars, are at high galactic latitudes, which means they have high proper motions, also high parallax because they're very nearby. So if you take a small beam in the sky, like which corresponds with SDSS and cross match, and you see, because SDSS is spectroscopic, they can tell you which of them are stars, which of them are galaxies. You can actually cut on this apparent motion and reduce star contamination down to about 0.1%. You get about 1.8 million galaxies. You can then also cut and remove anything that looks like an extended source, and then you get something that looks more isotropic. It still has quite a bit of structure, and this because this is a very shallow catalog. It's the median redshift is like 0.15. But this is in equatorial coordinates. So you see the maximum dipole in this catalog. It's actually just about 6 degrees from the CMB dipole. The amplitude is so high that if this was kinematic, the velocity would correspond to 3,600 kilometers per second. But there is also something called the clustering dipole. So it is not fully kinematic. And once you account for all of that, then the velocity, but this is from cosmic variance, it's from the model, etc. And this is not statistically significant at all. But even in a shallow catalog, you see that. So I wouldn't say this is a tension or anything. It's just curious that this catalog has a dipole in the same direction. More recently, Nathan Seacrest, who's an expert on quasars at the US Naval Observatory, he contacted us with this CatWISE quasars catalog, which after we did all the final selection, it has about 1.35 million sources. So and it has a redshift distribution which you can quantify from SDSS, and as you can see, it's the median redshift is greater than 1. It's very uniform in the sky, except for places where you have to punch out hotspots like the large Magellanic Cloud and the small Magellanic Cloud, etc. You can see that the distribution of fluxes is actually a very good power law, as is the flux function. So the index of the flux function is really relevant only at the lowest edge of this flux function, and you can extract both these numbers, that is alpha, which is this index, and x from the data. And we did so, and because we had a large enough catalog, we did something called frequentist null hypothesis testing. We just scramble the data, we apply selections according to aberration and Doppler boosting as expected. And so if this is the size of the dipole estimator, the dipole from the least squares estimator, if it was according to the CMB dipole, this is what you should expect. What we see in the data set is this. This corresponds to about a p-value of 5 times 10 to the power minus 7, which is 4.9 sigma one-sided. And as you can see, the direction is still within like 20 degrees of the CMB dipole. This dipole is so clean to the eye that if you just set a specific, a color range for your catalog after you make a heel-pi map, you see the dipole by eye, and it's twice as large as you expect from the CMB. So I earlier quoted velocities. I would like to remind you, I don't know about those velocities. I don't know if the Ellis and Baldwin formula is strictly speaking correct.
Ramesh, can I interrupt?
Sure.
Yeah, so how did you, can you give some more detail of how you did the simulations to produce this plot, the one on the left?
So we actually, our final limiting magnitude was 16.4. We take sources out to 16.5. Then we scramble the data in right ascension, which means that, sorry, not in right ascension, we just scramble it in the sky. And then we apply a flux cut where each flux, the flux in the direction is shifted by the Doppler boosting, and then we move the sources in that direction. We add an additional angular term according to this expression. So we are putting in the expected dipole from the CMB dipole into the data. according to the Ellis and Baldwin formula. Well, not the Ellis and Baldwin formula, but the effects that go into the Ellis and Baldwin formula. And then we are estimating what is the dipole we should get from the catalog. And it's less than half the size of what we actually observe from the data. So I mean, I will not claim that this cannot be a systematic or anything, because astronomical data sets are full of, things we don't understand. For example, the galaxies in a fixed direction in the sky, and there is dust extinction, etc. And these are, but we tried, for example, using different dust extinction maps, etc. And these, the amplitude of the observed dipole is not affected by this at all. And maybe there is something interesting in that direction. And actually, many authors have been finding. So these are, some of the results of ours. But for example, Costas Mikas at the University of Bonn, they looked at Rosat and Chandra X-ray clusters, and they see an anisotropy not that close to where we see, but within 20 degrees of the same direction. People have also looked and seen, and so when I spoke to Dominic Schwarz, for example, one of the things is that there is something happening in that direction. One of the things that's happening in that direction is if we take this frame in which the CMB becomes isotropic, so the dipole vanishes as the rest frame of the universe, then actually all matter in small shells around us appears to be moving with respect to that.
So it means you're making a huge jump between very low Z and very high Z when you make these statements, right? Mikas is Mikas working at high Z or low Z?
They're working at a median Z of about 0.3.
0.3.
It's low Z compared to
quasars, right? So okay, so just to put this in context, right?
Yeah. Thanks for pointing that out. But it's very hard to control. You cannot construct a catalog at exactly the Z you want, right? You take data and you try and get
The supernovae interpolate essentially from low Z all the way to high Z, so you have some control, right?
Yeah, but well, so I'll be coming back to supernovae in the end. So many observers in many different data sets, space-based, ground-based, infrared, radio, and X-rays are seeing anisotropies in this direction. And there's something going on. And what I want to say is, for example, my collaborator Roya, back in 2010 itself, had worked with R. Brent Tully of the Tully-Fisher relationship and a PhD student, etc. They've looked at the 2 Mars redshift survey, and they used an orbit reconstruction algorithm to reconstruct the velocities of shells around us with respect to this frame. And they keep finding that the shells, it doesn't really converge to the CMB rest frame. So this is the velocity of the local group. What they're asking is each shell accounts for what fraction of this velocity according to Newtonian gravity, the perturbation theory in people's textbook. And statistically, this is a marginal effect. It's within 2 sigma compatible with convergence, but there is a residual effect. They had also looked actually directly at supernova data itself, Union 2 catalog, and there again, you see that within 2 sigma, it is the bulk flow as you go in larger shells in redshift converges. Within 2 sigma, it is actually compatible with what you expect from the lambda CDM model, but there is some excess there. You can say that out to a redshift of 0.06, the outermost shell of the survey is still moving with a velocity of about 260 kilometers per second, and this result has actually been reproduced by Fint et al., which is a group led by Saul Perlmutter, with new data, and they find the exact same thing. But statistically, it is marginal, and it's compatible with the model. That's one way to look at it. For example, these authors have used, they have reconstructed the peculiar velocity field from the density field using linear perturbation theory. Which is the assumption that there is a background isotropic space on top of which everything works according to Newtonian gravity. And there again, they report that we find an external bulk flow is preferred at 5.1 sigma level. The best fit has a velocity of 159 plus or minus 23 kilometer per second towards L equals 304, a specific direction. This direction is actually quite close to the CMB dipole. As I showed you.
If lambda CDM is correct, it should be around 100. Is that correct?
Yeah, if lambda CDM is correct, it should be around 100. And yeah, so you would think this is not a tension. I mean, yes, with respect to the model, this is not a tension at all. But for example, with the 6-degree field galaxy surveys, velocity survey, also an anomalous bulk flow has been reported, but this is only reported in a conference proceeding so far. So yeah, this is not a significant tension with the model, but I want you to think about the ontology of this. I'm saying all matter. So this model, for example, that reconstructs this says that all matter in the local universe out to about 1 billion light years around us is moving with a velocity of 159 plus or minus 23 kilometer per second with the rest frame of the universe. And this 159, 23 kilometer per second is not that small a velocity. It's like 15 times the escape velocity of Earth. It's like 5 times the velocity with which the Earth is moving around the sun. So think about it. Maybe it has some relativistic consequences. And that's what Christos Sagas actually says there are. So Sagas is a mathematical relativist, and he uses actually something called the peculiar Ray-Chowdhury equation, which I can tell you about later. And what he does is he starts with an almost FLRW universe, then he perturbs it with peculiar velocities, and then he examines the geometry of that using the peculiar Ray-Chowdhury equation. And what he states is that if an observer is sitting inside this bulk flow, if you measure the deceleration parameter, the monopole of the deceleration parameter will get modified by how fast the flow itself is growing. Because a bulk flow means there is an overdensity on one side and underdensity on other side, and if the rate at which the overdensity is growing and the underdensities are growing are different, then the flow itself will accelerate, and that will have a geometric consequence, as in it will affect the local expansion rate. And the other thing is, he says, is if the observer is actually moving with respect to this flow rest frame, then you will actually see a local scale dependent dipolar modulation. So these are actually extremely interesting papers. Very recently, Christos has done a side-by-side general relativity versus Newtonian gravity calculation, which shows which terms show up in this. And if you're interested in that sort of thing, I would recommend you read this. So he puts this in words. This implies that observers experiencing locally accelerate expansion as a result of their own drift motion may also find that the acceleration is maximized in one direction, minimized in the opposite. We argue that typically a dipole anisotropy should be relatively local, and the axis should probably lie fairly close to the one seen in the spectrum of the cosmic microwave background. So we look for this effect.
So just to understand, I mean, I just want to understand the statement there. The statement is that there is an anisotropic acceleration. Is that the statement?
Yeah, the statement is that, well, so Christos works in a framework of, he works with like the Einstein field equations. He's a relativist. Mm-hmm. So there is the acceleration is always with respect to a frame, and this is a coordinate invariant approach. So you pick an observer within the flow, and what the observer observes as the local Hubble flow, the Hubble law will have a dipole anisotropy that's local, and that this will make it look like the universe is accelerating very fast in one direction and slower in another direction, and then in directions in the opposite direction, and then in directions perpendicular to that also, depending upon if the flow itself is accelerating or not. Even if the global universe, which might have an FRW description, is decelerating, it can look like the universe is accelerating simply because you're sitting in the middle of that bulk flow.
So my question is, but from that statement, it looks to me that what you would observe for the acceleration is anisotropic in the sky. Is that true? I mean, but
exactly. Exactly. As long as you pick a correct observer frame. So I will.
But we already so the data for instance the let's say the acceleration of the universe, the deceleration parameter, that is it known whether it is isotropic or anisotropic? Is there a dipole that has been looked for in it?
Yeah, so we actually looked for it, and I'm about to tell you about it, and others have. Let me just say first that we looked for this using a maximum likelihood estimator. So we looked for a dipole in the deceleration parameter, And what we found was that the dipole is actually statistically significant at the 3.9 sigma level. It is 50 times as large as the monopole, out to a redshift of about redshift of 0.1 or so. And the monopole is compatible with 0 at about 1.4 sigma. I'll give you more details of this analysis later. The conclusion we wrote in this paper is that the significance of Q0 being negative is less than 1.4 sigma. And we are like, so cosmic acceleration is just an artifact of us being inside a bulk flow. We are non-Copernican observers. And we said dark energy does not exist. Then to test Christos's hypothesis, we actually, in this fit, we had just fixed the dipole direction to the direction of the CMB dipole. We tried to vary it a posteriori. We don't have enough data to actually fit it all at one go and make statistically strong statements. And we actually find that it is within 23 degrees of the CMB dipole. So this kind of seems like a prediction by Christos, is confirmed by the data. And, so the dipole is much larger than the monopole all the way out to redshift of 0.1. And the monopole is essentially compatible with 0. So we tried to say that dark energy does not exist, and then this got us into like a kind of funny debate, and I'll tell you the reason for that debate. The thing is, in the standard cosmology, you have so the relation, the equation. Yes.
I got confused with the so this is a second work, is it? You had the previous slide was showing 1.4 sigma.
This is 1.4 sigma for the monopole.
For the monopole, okay.
Yeah, and the dipole is so. Now let me tell you why we said this. Because the equations of general relativity are these extremely complex equations that no one solves, and it is really a geometric Riemannian geometry formulation of gravity. To do cosmology, what we do is we assume this side of the equation is completely isotropic and homogeneous. Then this will give you can describe all of space according to just one scale factor, and all your clocks remain synchronized because that's the only dynamical degree of freedom within the system. And this then gives you the Friedmann equations, which is what are used for cosmology. Now you can divide these parameters like the density of matter, etc., which if this side is completely isotropic and homogeneous, are trivially well defined. And you can actually divide it by the critical density, and you get these standard parameters in cosmology. The current claim is that omega m is 0.3, omega lambda is 0.7, and all of this should add up to 1. However, if this lambda that you can add to this equation due to something called general coordinate invariance, the laws of physics are coordinate invariant. It's the same thing that quantum gravity people call the diffeomorphism invariance. If this lambda can be is in this part of the equation, you can also get it from the vacuum energy of the quantum field theories that describe this the particle physics that makes up your stress energy tensor, which is all the matter we know about. So if you try to calculate it from quantum field theory, I don't think these can be actually calculated. Quantum field theories are not that rigorous. But you can make order of magnitude arguments, and the order of magnitude argument is that the value of lambda that is calculated from quantum field theory is about 10 to the power 120 larger than what has been measured in astronomy. So people have tried to explain this using anthropic fine-tuning and such ideas, like there's a multitude of universes, and only universes in which human beings can exist because galaxies have to form, etc. That is how we get the small value of lambda. So I don't know about all of that, but Subir has noticed another thing, which is that the only dimensionful parameter in this equation is the present day value of the Hubble constant. And so the cosmic sum rule, basically what you're calling lambda from cosmology is just 1 minus the other terms, and its scale is set explicitly by the present day value of the Hubble constant. And so Subir described it as there is a non-zero vacuum energy of just the right order of magnitude to be detectable today. And he put this in this interesting paper he wrote back in 2008. What he left unsaid and what he uses to motivate these sort of tests of isotropy is that he believes this is an observational error, this lambda. So I'll tell you how we did this analysis with type 1a supernovae. One of the things about type 1a supernovae is
before you go ahead, one question. So in the 1.4 sigma and the 3.9 or 4.6, I can't remember sigma. So that you had, what is the observational data that you're using to get this? Is it supernovae or the standard things that people use to get the cosmological constants?
We're using something called the Joint Analysis Catalog of 740 type 1a supernovae.
Yeah, fine. I just didn't see that. Thank you.
Okay. So,
but Ramesh, if I can jump in there, right? So basically, I think the claim is that you've determined Q0 below Z equals 0.1, right?
Yeah.
Like in any of these supernovae, like that gives you essentially 200 supernovae, maybe a bit less, 150, is it? In JLA?
Actually, more than half of the 740 are. So I have a diagram. I mean, I am getting to these.
You're going beyond Z equals 0.1, right? Presumably.
Yeah. Most of the supernovae are actually at a lower redshift.
Right, but so you're determining Q0 at slightly higher Z than 0.1. So it's, I mean, like it's very difficult to determine anything at 0.1.
Yeah, but I think Owen,
the statistical errors are just so large, right? This is so basically it's just, I mean, it's probably you're going to Z equals 0.3 or 0.4 to determine Q0.
Yeah, I'll get there.
I think the argument can be applied also for the determination of the cosmological constant, though. That same argument. So if you take that at face value, I think one can take this at face value, and that I think is the sort of the Saga's
I know
argument.
If you work with Pantheon and you go to like 0.1, you can't even determine omega M0, right? It's you can't, it's impossible, right?
So I agree with all of that. Let me just get through the story and then you can interrogate me. Okay, so supernovae are basically type 1a supernovae are thermonuclear explosions. You believe it's some star that is at a sub-Chandrasekhar mass limit, like a white dwarf, and then it is accreting mass from a nearby companion. Just as it crosses the Chandrasekhar limit, it explodes. And so this is what they're believed to be. So because of that constant is there, people believe they're standard candles, but in fact, they're actually not. If you look observationally, for example, in this Callan-Tololo survey, what they find is that there's almost a 1 magnitude difference in the brightness of supernovae, to which we know the distances are the same. What they have, however, noticed is that the brightest ones fall off the slowest in the sense if you track how bright these objects are in the sky over time, the brightest ones get dimmer in the slowest period of time, whereas the dimmest ones actually fall off quite fast. So then you can, because this is some empirically observed thing, you can correct for that, and then the scatter reduces to about 0.15 magnitude. And there is an additional thing called a color correction. And so they're called standardizable candles. We don't theoretically understand why this thing is happening, why there is stretch and color dependence on the absolute magnitude. So we believe they're standardizable candles. You can reduce the scatter quite a bit. That is the idea. The idea is that in the latest compilation of data, whether it is Pantheon or JLA, they supply MB, they supply this stretch factor and the color factor. You can construct something like this where the absolute magnitude of the supernovae are unknown and it is actually degenerate with the Hubble constant. And you can then compare this against a theoretical model where your luminosity distance is calculated from theory. So the Friedmann-Lemaitre equations or something. So
just to jump in, Ramiz, right? So there's an ongoing debate at the moment about corrections for the mass of the host galaxy of the supernovae and whether this makes a difference or not. So like over the last 20 years, right, as things move on, they find these corrections for supernovae, right? So in the beginning, things were very naive. There was some intrinsic dispersion. Then they corrected for color and shape. And then now they're correcting for, the host mass, the host mass galaxy, the mass of the host galaxy. And they'll find other corrections as they move on. So I think it's a set of working assumptions.
Yeah.
Right? So in some sense, you're completely right. These are standardizable candles. And you have to take them with a grain of salt.
Yeah, I agree. So yeah, the source of the scatter around the line is not really known. And for example, if you look at Perlmutter's Nobel Prize winning paper, they used actually the observable. So the redshift was corrected to the local group frame, where the local group is moving with the 620 kilometers per second, and they expressed their result as higher redshift supernovae were found to be dimmer than the lower redshift supernovae compared to what would be expected in a lambda equals 0 universe, which is that the lambda equal to 0 universe, the data would fit this line better, but the data fit this line better. You can see there's quite a bit of scatter around here. And one of the interesting things is the statistical method they use. They construct a chi-square, and because the scatter is actually very large, you don't get a good fit. The chi-square by degrees of freedom is always much larger than 1. They add an intrinsic scatter term to the denominator and adjust it by hand until you get a chi-square by degree of freedom to be explicitly 1. Now, mathematical statisticians have always had problems with this, but you have to understand back in 97, statistics is an empirically evolving science. So back in 97, people did not really know about trial factors, etc., extremely well. So this is reasonable, but it is a pretty ad hoc procedure. The other thing I want you to notice is that if you plot all these supernovae in the sky, especially the low redshift ones, they were pretty much in the direction of these anisotropies we are seeing. Now, in 2014, they actually finally made the joint light curve analysis catalog public, which has these, which gives us the prescription on how to compare, how to build the distance modulus, etc. And they give you the redshifts actually already corrected to the CMB frame. And so Subir and his master student then decided to do a likelihood-based analysis, which is you write down a likelihood of probability of data given model, where which is then split into probability of these color and stretch distributions, medians given the cosmological parameters, and then the cosmological parameters. And you look at how the data are distributed to pick a functional form for it. This is a frequentist analysis. The advantage of writing down a likelihood like this is that it is still analytically integrable, so you can get confidence intervals straightforward from the analytic form of the likelihood by the Neyman-Pearson lemma. So, and then you can simultaneously fit for your cosmological parameters and all the parameters that go into your candle standardization. And so Subir, they did this analysis and they found that the evidence for acceleration was actually less than 3 sigma. So it was in the domain of a statistical fluctuation. And this was, of course, because Subir doesn't like dark energy, he picked a fight with it. And he basically said this is a statistical fluctuation. So this got Rubin and Hayden to write a rebuttal to this paper. Rubin is Saul Perlmutter's PhD student, saying that Subir assumed that these color and stretch distributions are redshift independent. And they argue that you should actually allow all of them to be both sample and redshift dependent. And in the process, so this model is 10 parameters. If you allow redshift dependencies and sample dependencies to all of this, you get a 12 parameter model. Once you do, a 22 parameter model, you get additional 12 parameters. And once you do that, the statistical significance increases to 4.6 sigma. Now, there's an interesting thing to note here. It is that these 3 terms together which make the standardization of the candle. So you have to assume that this is independent of redshift, that this does not evolve with redshift in order to extract cosmological parameters. It should not evolve with look-back time. They're explicitly arguing that these 2 terms now evolve with redshift. There is actually quite a bit of observational evidence that this also evolves with redshift and that the whole of dark energy is a mistake. But in the likelihood model that they use, they don't allow this to evolve with redshift. If you do, the evidence just completely vanishes, because what you're basically saying is they're not standard candles. Right?
So wait a minute, Ramiz. This would be dark energy as a mistake from the perspective of supernovae, right?
Yeah.
So you have some other pillars which dark energy is based on.
But all of
and unless you're going to take them all out in one go, these statements are like like they crop up every few years, and it's effectively a type of noise, right? It's very interesting. You get into the technical details of supernovae and the assumptions and stuff like that, but BAO also has to come out and CMB also has to come out.
for the
big picture.
Yeah, so you actually have to put in the Friedmann equations and assume the cosmic sum rule. So what you're essentially measuring is 1 minus omega m minus omega k, etc. I will comment on it briefly towards the end.
At least, but I think there is
and also the
evidence that the
ages,
universe is flat, right? I mean, the cosmic sum rule that you're talking about is coming from the universe being flat. So that I think is that I think is independently known, isn't it?
The cosmic sum rule comes from the idea that the universe, it is a property of the Friedmann equation. So it's exact isotropy and
Correct.
homogeneity.
No, that's fine. Exactly. But even given that, I'm saying that from CMB you do get the constraint that omega k plus omega lambda plus omega matter should be
flat,
1. So that is that constraint is
no, the
independent of
CMB
this, I
does
would
not
say.
say the CMB does not say any of that should be 1. The CMB assumes it should be 1 because you're fitting a Friedmann limiter model.
Right, but I'm saying that
also more recently, for example, Joseph Silk, Eleonora De Valentino, Alessandro Melchiori, they have shown that if you just let the CMB omega k parameter float, the universe no longer looks flat; it looks close to 3 sigma, right? So
right. Yeah. I mean, but basically what I'm saying is that it's certainly not the case that the matter alone can explain CMB. That I think is fair.
Well, also the age of stellar objects as well. So we have an estimate of the age of the universe from globular clusters. It's like 13.5 gigayears, right? Once you get rid of dark energy, you also have a problem there as well.
Again,
I'm not a fan of dark energy. Let me also say that.
No, I think it's robust. The reason dark energy is robust is because it's robust across multiple data sets and observations.
CMB, I think I would.
Hello, can I interrupt?
Sorry.
Very exciting discussion, but I think since we have a time frame, we will let Ramiz finish, and then we can continue with the more exciting discussions.
Yeah, I would love to continue arguing, but maybe
There's nothing to argue about this, Ramiz. It's dark energy. There's nothing to argue.
Sure. So the basic analysis we did is the luminosity distance in exact FLRW universe can be given by these Friedmann equations, and it can also be given by a Taylor series expansion, which is you write down it in terms of the Hubble parameter, the deceleration parameter, the jerk, and the curvature energy density, etc. And for the depth of the JLA catalog, which is about maximum 1.4 redshift of 1.4. This is precise to this within like 4%. So it makes no difference at all which you use. If you assume exactly FLRW, this is how you get the deceleration parameter. What we mean by fitting a dipole to the deceleration parameter is we turn the Q0 into a monopole and a dipole component separately. The dipole component has a scale dependence. The statement that this is the dipole is large at small distances corresponds to the fact that the scale we fit is rather local, corresponds to a redshift of 0.1 or so. So funnily enough, this also got us a rebuttal from David Rubin, who's, like I said, a Sol Permuter's PhD student. And what he does is he basically reproduces our result. He finds the dipole at a high level of high significance. Then he does a thing where he corrects the redshifts towards the CMB rest frame, and then the direction of the dipole changes. Then they also correct the supernovae for peculiar velocities, and then the monopole acceleration gets restated. So we have recently written a response in the form of a review where we have carried out the Hubble diagram fit in 4 configurations. One is in the local group rest frame, which is like Sol Perlmutter did in his original paper, in the heliocentric frame, because that's the frame with which we have access to, because that's where the sun is. The CMB frame without peculiar velocity corrections to the data, and the CMB frame with peculiar velocity corrections to the data. And it's clear. These papers are fun to read. If you want, you should. And as you make these corrections, the evidence for acceleration increases. So let me point out to you what these corrections are. The idea is this: because the universe is expanding, there is a cosmological redshift, which is given by this. And then because you are moving with respect to the rest frame of the universe, there is a special relativistic correction like this. And then because the supernovae are moving with respect to the rest frame of the universe, they're inside this bulk flow, there is another special relativistic correction like this. And so you infer this Z from the measured Z using these two things using a flow model. And so to do this analysis, we actually looked at how the data was disseminated, which is, you see, they give you a redshift in the CMB frame, and they give you a redshift in the heliocentric frame, and you can, so you can use this expression to subtract this out, and we find that the corrections of each supernovae on a supernova by supernova basis has been corrected by velocities that correspond to the flow of matter, right? The interesting thing is this: they use the model by Carrick et al., which, like I said, they report 5.1 sigma evidence for an external bulk flow, but within the data, at the threshold of that, they stop correcting. So, and so these models they use are these models, and you can see that this is in tension with lambda CDM. There are velocities corresponding to, so this is an earlier catalog called SMAC, which is what they cite, but late in private conversation, they mentioned that this is the Carrick et al. Model, and it goes up to 0.067. And it has an external bulk flow of 159 kilometers per second, but they don't have data, so they leave it uncorrected, right? So what I want to say is the data as publicly disseminated imprints a picture in which a 300 megaparsec volume, that is a 1 billion light year volume around us, is smashing into the far field universe, which is arbitrarily treated as at rest at a velocity of 159 kilometers per second. And only once you make all of those corrections do you actually get any evidence for acceleration from type 1a supernovae. And in fact, the key Hubble tension papers also rely on these corrections if you read them carefully. So in our the most recent review that we wrote, because we were invited to do so in European Physical Journal Special Topics, we have traced out the history of all the major supernova analysis. And the basic idea is that they were using this constrained chi-square, adjusting the error bar method, and they were throwing out quite a bit of outliers, as 3 sigma outliers. The method for standardizing has changed. Also, earlier they were using the local group rest frame, but later on they switched to the CMB frame. Then they started applying supernova by supernova peculiar velocity corrections. The first papers, they argued that lensing is not a significant systematic. Then they started adding uncertainties to the systematic term to account for lensing, and that has also changed. And so if the motivation for Subir's 2015 paper was to actually treat this uncertainty, which is independent of redshift, better, there are two other uncertainties, one which falls with redshift and one which increases with redshift, which are fixed by hand and are often varied between analyses. And, you know, in the final 740 supernovae that make it to the JLA catalog, it contains about 50 of the original supernovae from the original papers. This is each supernova exploding is data we are gathering on the fly, and it has to slowly accumulate. And I'm just saying, over the years they've changed many aspects of the analysis, which according to these figures and these papers strongly suggest that these changes account for all evidence for acceleration. You may wonder why I'm saying this. What if we use Christo's hypothesis and we fit exactly what he says, and we say dark energy doesn't exist? What exactly are we saying? There is of course the question of whether standard cosmology is consistent. So there's been this debate within literature called the back reaction debate. On the right side you have George Ellis and who wrote the large scale structure of space time, etc. with Stephen Hawking. Rocky Kolb, who wrote who's the first author of the early universe, which is a textbook, Kolb and Turner. And on the left side, you have Robert Wald, etc. And they keep debating whether lambda CDM cosmology makes any sense at all. The basic idea is this: if the universe could be described by the Friedmann equations, it has to look like this. And so describing a universe that looks like this with a metric designed for a universe that looks like this is like describing the real Earth as a perfect sphere. And for example, peculiar velocities, according to Christo's sagas, according to Charles Dyer, etc., are differences in the expansion rate of the universe, because what this statement really means is that all you can do is zoom in and out. With respect to time, all observers can only see every other observer either increasing their distance with them or decreasing their distance with them. That's what the solution really means. How does this kind of a universe evolve according to general relativity? The math is too hard and people are still trying to figure it out. But most of the inhomogeneous people cosmology are openly skeptical of dark energy, and half of them are skeptical of dark matter also. I find their mathematical work quite rigorous, so I think you should look into it. For example, the tools of cosmology, such as n-body simulations and cosmological perturbation theory, they don't do full GR physics. So there is quite a bit of circular logic in interpreting data from a universe like this in terms of a metric that's designed for a universe like this. And if you will let me take this Earth as a perfect sphere analogy a little further, because peculiar velocities are forbidden in a Friedmann limiter Robertson-Walker universe, you can think of it like a small mountain on this perfect sphere Earth. And the CMB dipole is like the sea level. The CMB rest frame is like the sea level. Everyone is correcting their data, correcting their data towards the sea level to do the analysis to fit for the geometry of the Earth.
Okay.
What we are pointing out is that we do not know how far we have to walk to get to the sea level. We have convergence to the CMB rest frame has never been demonstrated. All surveys explicitly point out that there is an external bulk flow. And publicly disseminated supernova data has a cliff in it, in the middle of it, in the middle of the data. That's how I would put it. It's a very reductive analogy. I apologize. Very recently, you must have heard of, for example, the Hubble tension, which is that the Hubble constant has been measured at redshift below 0.15, and it's at 5 sigma or 4.5 sigma or so tension with the CMB value. It turns out in the universe, if you treat each of these peculiar velocities as just a difference in the Hubble constant, a difference in the expansion rate of the universe, there is not even a Hubble constant, let alone a tension. So the Hubble constant has a 9% variation in the sky. So I think Eoin O'Colgan, who's been on this call for a while, they also have a paper pointing this out. There is a 10% variation in the sky. And so claiming to measure the Hubble constant to like 1% precision or whatever is like claiming to measure the radius of the Earth to a precision less than 23 km per second. It no longer represents a real system. It is not a well-defined thing. And it is just massive confusion, right? So this is my conclusion. The number clouds of flux-limited catalogues in radio and infrared all indicate somewhat significant, up to 4.9 sigma, tensions with purely kinematic interpretation of the CMB dipole. Hopefully, I'm hopeful that the square kilometer array and Euclid can set this to rest by testing in the future. Convergence of the local bulk flow towards the CMB rest frame has never been demonstrated, and this is a case for precision testing the CMB dipole with future missions like CMB Bharat, if you're planning to do that. And let me just go on a limb out there and say the CMB rest frame probably does not exist. Okay, we used to believe the universe had a center and that the Earth was it, and we were obviously wrong. Now we believe the universe has a rest frame and the CMB rest frame is it. I think the next generation of cosmology will have to somehow abandon this idea, especially since general relativity was explicitly constructed to say there are no special frames of any kind. Neither inertial frames nor acceleration frames, nor accelerating frames. So type 1a supernova ship with pre-corrections and are being continuously adjusted. Lambda CDM cosmology is just an ansatz, and dark energy was an artifact of that idealization. Very recently, Peebles has put out, his mission statement for the future of empirical cosmology. He calls Lambda CDM a very good approximation to reality. You have to see these things to believe it. But that is it. So this is my conclusion. But like any Marvel movie, I'll have an after credit session. I'd like to refer you to this paper by George Ellis, which was written in 1987. And these equations that supernova cosmologists started using in 2011 to correct their data for peculiar velocities. This is the first time in literature that I found a reference to these equations. So it is there in section 4.3. And they have a detailed description of basically the fitting problem of cosmology, the fact that the underlying universe is not homogeneous or isotropic, and we are fitting an isotropic homogeneous model to it. So it's like fitting a perfect sphere to Earth, and they discuss this. It's an almost philosophical paper, but it has such clarity of thought. And this is one of the marvels of cosmology, because about 10 years before dark energy was discovered, George Ellis almost has predicted with the correct equations and so on, what the supernova cosmologists will have to do to data to fit it to an FLRW model. So yeah, this is my conclusion. Thanks. I'll now take questions. Thank you.
Thank you, Ramesh, for an exciting talk. So now we can have all the questions and discussions.
Yeah, so I'll ask a question about the Sagas paper that you mentioned.
Yeah.
Which was so there is the statement there that this, if you have a dipole, you can. So what is the precise statement of Sagas? Is it that if you have a dipole, if the universe is really a dipole, and if you try to model it using an FLRW, you would end up simulating acceleration? Is that the idea?
No. So his statement is like this: if you have a universe that is in the far field FLRW, but you have local peculiar velocities. So you have local peculiar velocities, and you study the geometry, or the space-time geometry of that. Then from within the flow, the rate of growth of the flow will also look like the universe itself is accelerating, because there is nothing called absolute space, right? When we think of a bulk flow, we are thinking of an isotropic homogeneous space in the background that is expanding according to Friedmann equations, and then we are thinking of matter moving on top of it according to some gravity, which in the standard model is actually Newtonian gravity.
So in his universe, so far away, that is sufficiently far away, it's still FLRW. Is that correct?
Yes, it is explicitly a toy model. He constructs a toy model universe to study the covariant effects of phenomena like this. So,
but so for instance, I mean, the quasars that you're seeing are at very high redshift, right? I mean, very high means order 1.
Yeah, but, sure. But so the quasars should be interpreted with respect to George Ellis's 1984 paper statement that there is a mismatch of frames. The high dipole implies there is a mismatch, which is also explicitly what we see in the bulk flow, right? The rest
right.
frame
No, that's what I'm saying. But if that is the case, I would imagine that it doesn't look like it is stabilizing to FLRW even far away.
Yeah, so it could also be that the local bulk flow causes, shear in the cosmic, shear in space-time, which then modulates far-field observations.
Yeah, I mean, so I think it would be interesting to try and see whether there is a more, if you what happens to an observer who is in a universe which has a dipole all the way, let's say, and where you try to model that universe using FLRW, and then what is the observational signature? So I think that would be a more accurate way of going ahead. I'm not saying that this is not interesting. I mean, this is certainly very interesting. So I'm just saying that if if we could do that, then I think it would be also an interesting thing to try, because it looks like you do have a dipole fairly deep into the sky, and if that is the case, and we are trying to fit everything using FLRW. And
if I can jump in there, right, on a dipole that goes everywhere in the like very deep in the sky. Like we Chet and me and you and Lou, we have results basically at high Z in supernovae that you can just fit lambda CDM, and you can see that basically there's a discrepancy in the Hubble constant, and that seems to be there in quasars. It seems to be there in lensed quasars. I mean, it's not really significant. It's not 5 sigma, but it's essentially about 2 sigma discrepancy, or just about, in multiple data sets. So it's basically filling in the gaps between this super local stuff, because I mean, if we look at this slide, Q is essentially deceleration parameter, I presume, right? So it really is something very, very local. And then the quasars, which are this, they're extremely far away. And then in between, we should have all these other things that we see, right? And so we seem to be seeing that. And you don't even have to leave FLRW to see it. You can see the inconsistency within FLRW. But at low Z, there's a big fight. And the big fight is basically astronomers believe that they can handle all these peculiar velocities and not undercover the Hubble constant, but undercover basically the rate of expansion. So they're just going to keep correcting. And it's unavoidable. They believe
so
that
the only way is
so,
to plug the relation.
So I was going to say, like, you're getting into a fight that is you don't want to get into.
So I think you can win your battle at high redshifts. Z equals 1, let's say, or not even 1. I mean, anything about, let's say, a few hundred megaparsecs,
or 0.3 or 0.4, like, because beyond some redshift, nobody corrects for peculiar velocities or bulk flows or we don't even know what the universe, you know,
So for
we
instance,
don't even
in
have
our
maps
paper,
of the
we find
universe.
it at 0.34. Beyond 0.3, 0.4, I mean, supernovae already give you a dipole. So this is, that's what we actually saw in our paper. So
Without looking
anyway,
for
your
it.
talk was
Actually,
very
here I have a
interesting.
technical question, Ramiz, right? So you've got
Yeah.
3.9 sigma, right? But you're using cosmography all the way up to z equals 1.4. Now
Yeah,
we know that
we
expansions in
explicitly,
z are not valid beyond z equals 1.
actually,
Right.
we checked the validity of it, and it's valid within 7%, which means that the fit, you know, if we were using Pantheon, I agree it wouldn't matter.
Exactly. So if you take lambda CDM, right, and
Yeah.
you have z and z squared, you can
Yeah.
recover that to 1% through to z equals 0.7.
Yeah,
And you
so
can certainly push it further, but z cubed is 0.84, and that's only for omega m 0 equals 0.3. So I mean, the further you go,
I
so some
explicitly
of your
did.
3.9 sigma, I think, is an artifact of your cosmographic expansion.
No, I mean, if you use the, you know, the monopole term as exactly the Friedmann equations, and you fit for a local dipole, we still get a significant dipole. The issue is this cosmographic expansion is actually it is written down in terms of z, but it is explicitly an expansion in terms of the scale factor, and the scale factor at z equals 1 was half, right? So this almost works till z equals 2. It actually works very well till z equals 1.4. We checked this. You can fit the FLRW model, you can fit the cosmography, and you get exactly the same goodness of fit parameters due to any. And so Rubin
to 7%, right?
Yeah, 7% in the luminosity distance, but in terms of goodness of fit, because of this large intrinsic scatter, they're basically the same thing. So Rubin and Hayden also use this same.
I think this is a terrible expansion, and there's a reason for this. Is that, like, it's very difficult. Like, basically, okay, people like to work in the luminosity distance, but you can also expand h of z, and typically when they do like an expansion in z for h of z, and they also expand this way here, as Matt Visser does. But there's an inversion that has to happen. So dl is basically the integral of 1 over h of z dz. So each time you do an inversion, like, there's a couple of steps that go from basically the luminosity, like, let's say the Hubble parameter to luminosity distance. This may be a bit technical comment for most of the audience, but you're throwing away information each time you do this. So it's good to work with one, but not the other, right? Because there's all these.
People have tried all sorts of things. You can do a, you know, what is called a Faraday approximant.
You need to be very careful with this stuff. I'm not saying that you guys. We find all sorts of examples in the literature where people have done these expansions to z equals 2, z equals 3. They don't think about it.
So I agree with you that if this was going about redshift of 2, where the scale factor approaches 1, then we would have a significant. But at 1.4, which is the maximum of the JLA catalog, this is good within 7%, and 7% is below the, you know, the overall uncertainty.
I think that's an accident. I mean, there's no mathematics that. So, for example, Matt Visser has a paper with his co-author from 2007 where they explicitly explain why going beyond z equals 1, like, not, you know, all bets are off beyond z equals 1.
Yeah. Okay. I mean, sure, I agree with you. But so you can, you know,
because you're beyond the radius of convergence, basically. You're just.
Yeah. So we have also done fits where we use explicitly this expression, and then on top of that we add a dipole term to the luminosity distance, and you get the same statistical significance. It was just a question of we can't claim the universe is both isotropic and then still use the Friedmann limiter equations, right? So it didn't make sense to us. Also, Christos explicitly in his paper says it is the deceleration parameter in tilted Friedmann universes. So
again, I think this is a very local statement, right?
Yeah.
I mean, so your quasars are very, like, I mean, basically this.
No.
This huge anisotropy going through the universe, if you're right.
Possibly.
I mean,
yes.
and it doesn't have to come all the way down to low z.
Yeah.
Where at low z you've got to fight with some astronomers who feel that they can basically measure the rate of expansion.
But very surprising if at low Z you found homogeneity or isotropy, and then at high Z you found this axis or dipole.
No, you probably like, but it's a question of what anisotropies they are at low Z, right?
Yeah, I mean,
Are they
I
connected
agree
to
that
your...
I think the battle that Ramesh wants to win, I think it's easiest fought at higher redshifts.
Yeah, get it done there, and then
I agree that with these kind of searches, like I mean, these kind of these kind of ones, they're best fought at high energies because high redshifts, because there is something called this clustering dipole, which is the idea that matter can be distributed anisotropically locally, and that somehow doesn't affect space-time. And if that is something lambda CDM cosmologists believe. And it turns out if your catalog is shallow, that thing is very large. So then they'll be like, yeah, this is just a clustering dipole. So this battle is best fought with extremely high redshift catalogs. I agree with that.
Right. So did you read Ruth Durer's paper today by any chance? Just
Yeah.
She gave two options towards the end. Like, one is that we've got this anisotropy in the universe, and the other is basically there's some motion between, like, the average, like, let's say, of galaxies with respect to the CMB, and presumably isotropy would still be there, right? And so she was asking, she's trying to come up with some new method of differentiating these two, but I mean, it seems pretty clear that we're looking at an anisotropy, right?
Yeah.
I didn't understand the statement of the rest frame of galaxies and the rest frame of
the average. It was something like that. Yeah,
so that seemed like I could not decipher that fully. I mean, maybe it makes sense, but the second statement makes sense to me because it's a much more naive statement.
Yeah, I mean, it's very hard to look at the Einstein field equations and believe that space-time dynamics is driven by radiation and not matter, right? So, especially when omega m is much larger than omega radiation by a factor of 6 orders of magnitude or something. So I don't know why the radiation rest frame is the rest frame of the universe, even though we have not converged to it. I think.
One more comment. I read the People's article as well, and I was actually quite impressed because the first thing he introduced is that something beyond beyond lambda CDM was the cosmological principle. So he definitely put that on the table very early, and he sort of said that maybe lambda CDM is just a good approximation, and so in the Hubble constant we have like a 10% difference. It's not huge. So basically you had a 7% difference in your cosmographic expansion, right? So 10% is not exactly huge. So the anisotropy, if it is very large, it can't be, it's not a huge glaring thing. It's something relatively mild, right?
Sure.
The cosmology has got so far with FLRW, right? It's something, I guess this is back to Chetan's point, right? Is, how do you model this stuff?
Well, the way to model this, I think, would be the kind of questions you're asking would be to start with a Bianchi cosmology and ask questions like, oh, if we interpreted this as an FLRW cosmology, what would it look like?
Yeah, so I think that's a question I think it is worth asking, because I don't think people have really looked at the case where you're really looking at a universe which has this flow all through, and the sagas thing that you're talking about, as you were saying, basically he assumes that at far enough redshift it becomes again FLRW. But I think from the evidence that you're seeing,
Pankaj Jain at IIT Kanpur, do you know him? I think it's Kanpur, I'm not sure. He's at one of the IITs.
I think I've heard the name, but I don't know any cosmologists, unfortunately. I'm also from a particle physics background.
So very recently, he's built a model with super horizon isocurvature perturbation. So you have a perturbation that's larger than your horizon, which can cause all matter.
Has he built a model? I mean, I have seen papers of this type, I think, from Turner, but quite old papers.
Yeah, but I don't know, trying to explain an anisotropy saying it's a remnant of a pre-inflationary universe, like saying God made it that way, it's not
but I think God is already there in inflation anyway, because initial conditions is what it's for. So, I mean, we can't escape God here. So we might as well.
These super horizon isocurvature perturbations could essentially fit all the anisotropic data, and possibly it is a proof of concept that we can try. But I'm not very excited by that model. I'm more interested in the kind of stuff George Ellis thinks about, actually, but that's not.
No, but I'm just talking about fitting with what you're seeing. I mean, you're seeing and what we saw in our latest paper, which is that even at high redshift, there seems to be a dipole. So if you take it at face value, what happens? That's what I would like to know. So what I'm saying is that Sargas's model, because it relaxes to FLRW far away, I don't think that's the best way to model. If you want to get rid of cosmological constant, which I would love to, by the way, if that is the case, then I think that a better fit would be to try to fit, like let's say an observer is trying to fit an FLRW model or in a universe which is a dipole. What happens? What does he see? I don't think there is literature on that, as far as I can tell. But the Sargas thing is, like you said, it assumes that it becomes FLRW far away.
Yeah, I agree. These are all. So there is Haley McPherson and Asta Heinesen. Asta Heinesen was Subir's. She's now a postdoc at Lyon, and they are actually doing n-body simulations that are fully general relativistic and looking for these kind of anisotropies. And if you talk to them, they'll help you out.
Yeah. I've seen her paper from the
Einstein
2010.
toolkit.
Yeah. I saw her paper from last year, Asta's paper, but she leaves it at the stage where it looks at the anisotropic, the general universe. But it would be nice to see what happens if you fit an FLRW on top of that. That I think, an observer who tries to fit an FLRW on such a universe, that I think has not been done yet. Yeah. Anyway, thanks for the comments. I mean, this is a very interesting talk.
Can I ask a
There is
question?
a question. Yeah, Raghu has a question.
Sorry, I'm kind of an outsider. I just wanted to ask. Sorry if this question.
No. Please go ahead. Nothing to apologize.
Go ahead.
So yeah, Ravi. So I was just wondering. So this dipole, the matter dipole, is you say it is not kinematic and it is much larger than what you see in cosmic microwave background. So then, what is the implications for the data analysis of CMBR? I mean, how does this affect the?
Well, so we have tried asking the Planck collaboration to release their data without subtracting the dipole for the last 4 years, and it involves a lot of work because they just subtract it out in the beginning before they do other foreground subtractions, etc. So it is still not public, the CMB data with dipole in it, and I don't know about. But there is, for example, in the CMB at low L's, there is a hemispherical power asymmetry. There is the alignment of quadrupole, octopole, etc. And some of these, for example, inhomogeneous cosmologists like Wiltshire, they have suggested that this could be because a non-kinematic dipole is being subtracted out, assuming that it is kinematic. That leaves behind an artifact in the data, and that might be what they're seeing, etc. So, because now there is a crisis in cosmology, everything is on the table.
Okay. So, kind of, sorry. Do you imply that if you do the right way of analysis, you will not get the dark energy parameter from CMBR? Is it?
I don't want to make such statements. As long as you think of cosmology as parametric, something that you're estimating parameters, you might find parameters you don't understand, and then you can call them dark something. I'm just saying that it is probably not the kind of thing that you as a string theorist want to believe is making the universe a de Sitter space or something. And it is more like, if you measure the surface area of Earth and compare to its volume using equations for a perfect sphere, you'll see a mismatch. You can make that a match by adding an arbitrary lambda. What has that taught you? So that might seem like an unkind statement, but as a PhD student, I look for dark matter, and then I looked at cosmology. I realized all of this is made up. So that is my statement. I don't think we should think of cosmology explicitly in a concordance model sort of way, because the universe is once given. We can observe only one universe, and that has implications for how we do cosmology as a science.
All right. Okay. Thank you, Ramesh. Yeah.
Right. Actually, Ramesh, can I just make a quick comment on that? Right. So basically, lambda, right, fits inside a quintessence model, which you can think of as a generalization of lambda, right, for high energy theorists, and like you can prove in quintessence that H0 is always lower than lambda. And then it just tells you that like you're going to exacerbate Hubble tension. So in some sense, the fact that all local H0s that we're seeing, right, within FLRW are higher than Planck lambda CDM already tells you that quintessence is off the table. So like Hubble tension is really catastrophic for dark energy models. And then I think from there you can start inferring that maybe there's a problem with dark energy.
Yeah.
You know, basically, a lot of theories that we've constructed are now being challenged just by the fact that local H0 is high.
Yeah.
Yeah, I agree with that. But I mean, I'm not, like I said, I'm not convinced the local H0 is high. I'm convinced there is no local H0. You look in one direction in the sky.
It's within our framework. They're all statements are within FLRW, right? This is, you know, basically these you put on your glasses, and I completely agree with you. Right? We're on the same page, but
Sure.
Okay.
But for example, this Carrick et al. Peculiar velocity field reconstruction that assumes, you know, linear perturbation theory in something called the conformal Newtonian gauge, which is not a valid gauge choice under GR, and then also the masses of the galaxies that you see are extracted assuming that they're dominated by dark matter, etc. So there is a lot of model put into it, a lot of physics we don't know, and then you get something and you put that in the data and you get a narrow error on your a small posterior on your H and H naught. And yeah, I'm not sure. I don't want to say too critical things right now. I probably have gone overboard.
Oh, but Ramiz, what you need to say is that all BAO analysis and all CMB needs to be redone, right? That's essentially where we're at the moment, right?
Yes, much of it is actually circular logic. Like you have to put the FLRW model into BAO before you can extract the parameters from it. It's a little horrifying.
All right. So on that note, I think it is time to wind up the session.
Okay.
Thank you. It was nice talking to you, Chetan and Johan. I'm sorry.
It was nice to meet you. Yeah, it was nice
thanks
to
very
meet you,
much. It was a
Ramesh.
very good talk. Lots of nice details. Thank you.
Thank you.
Bye.
Okay.
Bye.
Bye, Ramesh.